Hi, and welcome to this second video on the AdaBoost algorithm. So in the previous video, right, we saw this AdaBoost algorithm following this template here. We're going to have a training data set of n training examples, x1 to xn, with labels y1 to yn, binary classification, so labels -1 and +1. If I have also a base learning algorithm A, then AdaBoost is a way to train multiple hypotheses using this base learning algorithm and combine them into, I guess, a stronger hypothesis based on them. And the basic idea is that we have some weighing, again, on the training examples. So you should really watch the previous video if you haven't done so far. You have a weight on all the training examples. It starts with being a uniform weight before you start. And then for t iterations, you're going to run this base learning algorithm A on the weighted 0-1 loss, where they're weighted according to this probability distribution, outputting a hypothesis HT. You compute the weighted 0-1 loss for this hypothesis just by summing over all the points that you misclassify and summing up the weights. Then you compute this magic constant alpha t, and then you change the weighing for the next iteration by taking the current weight and multiplying it with an expression that goes up for misclassified point and down for correctly classified points. And you normalize by a normalization factor set t. The final hypothesis is this weighted majority, where you sum over all the predictions made by these individual hypotheses, weigh them by their weights, alpha t, and this is the one that you return at the end. Right, so we saw this algorithm in the previous video and also an example execution of it, where we had this data set that you see up here. And then we ran 3 iterations of boosting, where you can see that it changes the weight on the points, here illustrated by the size of the points on the picture. Changes the weights of the points, finds 3 different decision stumps, and combines them into a final classifier that actually manages to get all these training data correctly. The decision boundary looks like this. So everything in the blue region, if you ask f for the value of a point, in here, the label of a point, you'll get +1, the blue class. And out here, you get -1, the red class. Right, so we saw this execution of AdaBoost, and in this example, at least, it perfectly classifies the training data after these 3 iterations. Right, okay, so what we wanted to do is actually to generalize this and show something general about AdaBoost. So the way we motivated AdaBoost was by saying that a weak learner is something that classifies data a little bit better than random guessing. And a strong learner is one that classifies the training data set perfectly, so gets all the labels correctly. And again, as I also mentioned in the previous video, this is not the original definition of a weak learner and a strong learner, but it's close to it. And this is the basic idea in showing that AdaBoost actually does transform a weak learner to a strong learner. So for this video, this is going to be sufficient. We just want to show that AdaBoost is basically a way of taking an algorithm that can classify data a little bit better than guessing and turning it into something like up here in the picture that classifies all the training data correctly. So this is just the definition we'll work with. Right, so AdaBoost can basically take such a weak learner and turn it into a strong learner. And this video here will be a very theoretical focus of this video, where we'll just focus on actually establishing this claim, proving that AdaBoost, if you give it a weak learner, it produces something that gets all the training data correctly. Okay, so to prove that, we have to be a little bit more formal. So a weak learner now is a classifier that for any weighing of the training data set, it will output a hypothesis whose weighted 0-1 loss is a little bit better than guessing, meaning that it's less than 1/2 minus gamma for some non-negative gamma, or strictly positive gamma, actually. So this is what a weak learner is. You can feed in a reweighing of the data set, and then it's promised to return a hypothesis whose error on this reweighing is no more than 1/2 minus gamma. Okay, so that's the definition of the requirement of a weak learner. And we will still, the strong learner is still something that perfectly classifies the training data. So what we'll show is that AdaBoost, if the base learning algorithm is actually a weak learner, one that always does better than random guessing, then once AdaBoost has run for enough iterations, it will produce a classifier F that has perfectly classified the training data, like we see here in this example. So this is what we'll try to prove. And this is a highly non-trivial statement. Good. So if we run it for enough iterations, it will perfectly classify the data. Good. So to try and analyze this, we'll introduce this notation that we call capital F sub t, which is basically the classifier that AdaBoost has produced after t rounds but before we take the majority vote, right? So we kind of, if we wanted to take the majority vote, the actual classifier after t rounds, we would take the sign of this weighted sum. So here we're going to also use the value of this capital F of t. So before we take the sign, this is going to be important in the analysis, this expression here. Okay, so capital F of t is just the classifier that AdaBoost would have produced after t rounds if you just ignore the sign part of the expression. Okay, so the final classifier, of course, when AdaBoost is done, is just f of x being the sign of capital F sub capital T of x, right? So the one after all the t rounds of training. Okay, so what we want to prove is that this final classifier here, right, that the 0-1 loss for this one, the in-sample error is 0, right? If we run for enough iterations, right? We want to prove that the average over all n training examples of the 0-1 loss, namely counting whether the prediction is wrong or not, this in-sample error, we want to show that this is actually going to be 0 after enough rounds of training. So to do this, the first thing that we'll try to do is that we will look at these weights that are being assigned by AdaBoost. And this was the formula from the AdaBoost algorithm for updating the weights from iteration t to iteration t+1. So again, recall that what we did was we took the previous weight and then we multiplied it with this exponential expression, x to the minus alpha t. This was this magic constant we computed, depending on the quality of the hypothesis learned in the tth iteration, times the label, times the prediction made by the tth hypothesis. And then finally, we normalize by this set t factor. So the first thing we'll do in the analysis is to, okay, let's try to expand this out so it's not really a recursive definition like the one we have here. So this is the formula from above. And what we can do is we can use the formula again on d sub t. So d sub t we can now write as d sub t minus 1 times this exponential expression again, but for iteration t minus 1, and also the normalization term for iteration t minus 1. So I just expand, I use the same definition on d sub t. Okay, now I can of course keep doing this on the, I can recurse again on the dt minus 1, all the way down until it says d sub 1, the very first one of them. And then what I get here in all these expressions, I get the product, I get a term for each of them from j equals 1 up to t of e to the minus alpha j, yi, then the prediction of the jth hypothesis on xi. And of course, what I also get here in the denominators, I get the product of these set j's. Okay, now d sub 1, this is I guess the last step we can go back. And here we know that the first weight that we put on everything is just a 1 over n. Right, that's the uniform weighing in the first round. So this is a 1 over n. And the nice thing about this product in the numerator, the product of the exponentials turns into the exponential of the sum. Right, just because when we multiply exponentials. So this whole thing here, that the distribution that we have in iteration t+1 is exactly 1 over n times the exponential function applied to the sum from 1 to t of minus alpha j, yi, hj of xi. Okay, and then we divide by the product of the set j's. And now in here you see that, well, if we ignore the yi, we have the sum from, so we can move the yi outside of the sum. And if we move the yi outside of the sum, then what we have left, sum from 1 to t of j equals 1 to t of alpha j hj of xi, this is precisely this classifier that AdaBoost has produced after t rounds of training, right? Without taking the sign, it's exactly this f sub t of xi. This is what, if you took sign of this would be the prediction made by AdaBoost. So this whole expression simplifies to 1 over n times the exponential function applied to minus the label times the prediction that you would have made on xi in iteration t just before you take the sign. And then you have this normalization term, still the product of these set j's. Okay, so I just moved it up here. So let's try to at least look at this to get some intuition on what is this expression telling us. So what we can see is, again, right, that if the label yi and this prediction you would make before taking signs, if they have the same sign, they're both positive or both negative, then the product here is going to be positive and you're going to have a minus in front. So the weight on the point, on the ith point, is going to be small, right? You have e to a negative number. right? So e to the minus, and in particular, the number that you have up here will become the absolute value of this ft of xi, right? The output of the hypothesis, or this combined thing that AdaBoost would have produced after t rounds before taking signs. Okay. And on the other hand, right, if they have opposite signs, so you're misclassifying the point, then the weight is going to be large, right? In particular, this term in here, the minus yi ft of xi, they have opposite signs, yi and ft of xi. So this will basically, the minus will cancel out with the opposite sign. So you just get the absolute value of ft of xi. So it will have a large weight and it will be larger, the larger this prediction is, the value that AdaBoost outputs before taking signs. Okay, so in some sense, right, this is just again stating what we also claimed in the previous video, that AdaBoost somehow puts large weight on points that are not classified correctly. And even more so, right, the weight is actually proportional to the prediction you would make before you take signs. Okay. So, right, what we wanted to prove is, of course, that the in-sample error is 0 after enough iterations. And what we've just established is something that is related to the weights on the training examples. So we'll try to connect those two things in the following, right? So how can we connect this expression to the one up here? Okay, so let's try to work a little bit with this 0-1 loss. Now, so the key idea here is to look at this 0-1 loss and then say, okay, the 0-1 loss here, I can also write it differently. So what we know is that the final f here, right, what it's doing is that it's going to take the sign of capital ft of xi, and that's the estimate it's going to return. Right, it's going to return the sign of capital ft of xi. Now, for this to be wrong, it must be the case that if I take the label yi and multiply it onto this prediction, then I'm going to get something that's negative or non-positive at least. So, right, because if the label, if ft of xi is 0, then fine, we still count as a misclassification up here. And this is also still going to count 1. If ft of xi is different from 0 and has the opposite sign of yi, then when I take the sign of ft of xi, I'm going to get a wrong prediction. But if they have opposite signs, the product is going to be negative. Finally, right, if ft of xi has the same sign as yi, then if I take the sign of it, I'm going to predict correctly. So I'm going to get a 0 in the 0-1 loss, but also down here, this will be a positive number, so I'll get a 0 for this indicator. So these are the same. Okay, so this is just with equality. Making a wrong prediction is the same as the product of this label yi and the prediction before taking signs being less than or equal to 0. Now, what I'm going to do now is I'm going to upper bound this by the exponential function applied to minus yi ft of xi. Right, so let's try to see that this is a valid thing to do. So, right, there are two cases I guess we have to worry about, right? There are two values that this 0-1 variable can take. And in the first case, if yi ft of xi is actually greater than 0, then this indicator becomes 0. So now you're comparing 0 to some exponential of something. The exponential function is always strictly positive. So this inequality is true whenever the indicator, the 0-1 indicator is 0. Okay, so that's fine. So at least it looks like the inequality is correct. We also have to check the other direction. What if the indicator is 1? So the indicator is 1 whenever yi times ft of xi is less than or equal to 0. Now, if this is the case, if this is less than or equal to 0, then what we have up here is we have minus this expression. So now we have e to a non-negative number. Now, e to any non-negative number is at least 1. So it's still, the claim is true because here we have 1 from the indicator random variable, and here we have something that's at least 1. So this inequality is actually a valid inequality. We can upper bound the 0-1 loss by the exponential function applied to minus yi times the prediction made by this AdaBoost output before taking signs. So I just moved it up, right? So the in-sample error is no more than the average over all n training examples of the exponential function applied to minus yi ft of xi. And now this starts now to look like something that we've just seen, right? Down here, we had the weights, the expression for the weights. And that's what you can see here. If you compare the two, right, you can actually see that this 1 over n exponential function also occurs down here in the weights. So there's somehow a relationship between the in-sample error and the weights. So, okay, so what we now also know is that when we go to the very last iteration, right, the dt plus 1, that's the iteration that we produce, or that's the weighing that we produce just when we stop. We know it's a probability distribution, right, because we always normalize by this set j factor or the set t factor. So we know it's a probability distribution. So which means that we know that if we sum all the weights in iteration t plus 1, then we're going to get 1. But we also, by this expression up here for the weights, what we're also going to get is the sum from 1 to n of this expression up here, right? So this is just by this rewriting of the weights that we saw before. Now we have that 1 is equal to this sum here. So what we're going to do is we're going to move the product to the other side. So now we know that the product of these set j's is equal to the sum from 1 to n, 1 over n, this exponential function. And now this starts to look like something, right? Because what we have here is exactly this upper bound on the in-sample error. Which means now that we know that the in-sample error of f, the final hypothesis, is no more than the product of these normalization terms, right? Just by rewriting. So the in-sample error is somehow bounded by the product of the normalization terms that you apply in each of these rounds of AdaBoost, right? This is really a really surprising connection, but nonetheless. Okay, so this means now that, okay, the in-sample error is no more than the product of the normalization terms. So all we have to do now to show that the in-sample error is going to be 0 eventually is to show that this product is going to be small. Right? So we have to prove that the product of the normalization terms get really small. Okay, so let's try to focus on this. How can we bound the product of the normalization terms? Here's AdaBoost again, right? This is the whole algorithm. And as you can see, right, the normalization terms somehow depend on this alpha t's that depend on the error t's. So the error t's is, again, the weighted 0-1 loss of the hypothesis trained in each iteration, and the alpha t's are these magic constants, right? So let's just move them to a new slide just to see we have the error t's somehow, something that we need to worry about, and we have the alpha t's here. The alpha t is the weighted 0-1 loss in iteration t of the hypothesis we trained, and alpha t was this constant here. And finally, the set t, the normalization term, is the sum from 1 to n. We take the previous weight in the previous iteration and multiply it with the change in weight on this point. Right, so this is this exponential to the minus alpha t yj ht of xj. Right? So these are the terms that we have. And now we want to somehow bound these set t's. Okay. So I just move the things up. We want to bound set t, and we have these things available. Okay, so what do we have? What can we do now? The first thing we can do is we can try and write out this set t to another expression. So what do we see here? So what we do here is that, let's say, okay, so there are two cases, right, for all the n training examples. There are the training examples that are classified correctly by the t hypothesis, and there are those that are misclassified. So what I can do now is I can say, okay, each and every one of the terms that are classified correctly, this expression just becomes e to the minus alpha t, okay? And so I can all the ones that contribute that are scaled by an e to the minus alpha t, all the ones that are correct, they're captured by this part of the sum here. You sum over all the points, you take the weight here, and then you take an indicator variable for whether it's classified correctly. And if it is classified correctly, you count e to the minus alpha t. Similarly, for the points that are classified incorrectly, so yj is different from ht of xj, meaning the product is -1, we get e to the alpha t as the term here. So the contribution from those terms we'll get if we multiply with the indicator for the label being different from ht of xj. Okay. Now this thing here we can work with, because what we see here is that let's split it into two sums. So I can move the e to the minus alpha t outside the sum. So here it is. And the sum of all the points, the dt of j times the indicator over here for the label being correctly predicted by the t hypothesis. Similarly, we have the other term where we have e to the alpha t, we move outside, and then we have the sum of all the points, the weight of it times the indicator for whether I misclassified the point. And now these two sums here are actually really nice, because as you can see here, the first one is just, if you look at what is the definition of the error, right? The error is the sum over all the points that are misclassified and then take the weights. So this is exactly what we have here in the second term here. So the second term is e to the alpha t times error t. And this one is just 1 minus that, right? Because it's a probability distribution. So here I'm summing all the points that are classified correctly, like sum their weights. So of course, the sum of their weights has to be 1 minus the error t. Right, so now I've rewritten this set t as e to the minus alpha t times 1 minus error t plus e to the alpha t times the error t. Okay. And we want to show that this is small. Right? We want to prove that these set t's, these factors that are used, we want to show that they're small. Okay, so now I can plug in what alpha t is, right? Because I have it up here by definition. Alpha t is a half log of 1 minus the error t over the error t. So the 1/2 turns into a square root. And in this first term, I have a minus in front of this log. So if I move the minus inside, I flip the numerator and denominator, and I get error t over 1 minus the error t. So this e to the minus alpha t becomes square root error t over 1 minus error t. The other term over here, the half becomes the square root, and here it's a little bit easier. It's just e to the alpha t, so we get 1 minus error t over the error t. So here we get root 1 minus error t over error t. And what you see here is that these two terms are actually the same. They're actually both equal to the square root of the error t times 1 minus the error t. Because this factor here, a square root of it cancels out with the denominator, and then we have a square root left. Similarly, over here, square root of this one cancels out the denominator. We have a square root left, and this we have twice. Okay, so now we have an expression that set t is actually equal to 2 times the square root of the error t times 1 minus the error t. This is actually the normalization term that we're using. Okay. Now we're almost done, right? Because we want to show that, right? So what we have is that the in-sample error, again, was no more than the product of the normalization terms, right? We already showed that. So, and now we know what these set j's, they are basically 2 times the square root of error j times 1 minus the error of j in the jth iteration. Okay, so now we want to show that this is small. And what we're going to use here is that actually we had a weak learner, right? Now we haven't used that assumption yet at all. But the weak learner assumption means that this base learning algorithm that we run in every iteration, what it's going to do is it's going to return a hypothesis whose error under this weighing is at most a half minus gamma. Right? That's exactly the assumption of a weak learner. So the assumption is that each and every one of these terms, this error j is no more than a half minus gamma. Okay. So to conclude now, what I'm going to claim is that this expression here, 2 times the root of error j times 1 minus the error j, is increasing in this error t. Until for every error t less than a half. Basically, what I want to use this for is to say, well, then this whole thing is upper bounded by if I insert a half minus gamma into it in place of error j up here. So just to see that this is an increasing function, the easiest way to see that something is an increasing function in an interval is to compute the derivative and see that the derivative is non-negative. So let's do the derivative of this expression here. The factor 2 stays outside, then by the chain rule, here I have a square root. The derivative of the square root is a half times 1 over the square root. The inner function is still the same, so the 1/2 cancels out with the 2. I now have 1 over the square root of the inner function, so 1 over square root error t times 1 minus error t, and then I have to multiply with the derivative of the inner function. The inner function is error t times plus or minus error t squared. The derivative of minus error t squared is 2 error t. The derivative of error t is 1. So this is what I get in here from the inner function. So by the chain rule, this is the derivative. And okay, so what I can see now is that if I look at error t for error t less than a half, then this term over here, since I take 2 times the error t, if error t is less than or equal to a half, or specifically if it's strictly less than a half, this is going to be strictly less than 1. So this is a positive term. Down here, error t times 1 minus error t, it's always a positive number. I take square root of it, it's a positive number. So the whole thing is a positive number, meaning it's an increasing function for error t less than a half. Okay. So since it's an increasing function, I can upper bound it by plugging in the largest value that error j can take. And we just said that this is a half minus gamma. So it's upper bounded by inserting a half minus gamma in place of error j here. And this gives a half minus gamma for this term. It gives a half plus gamma over here. And that t of these terms, so the whole in-sample error is bounded by 2 times the square root of this 1 half minus gamma times 1 half plus gamma, and the whole thing raised to the t. Just multiplying it out, the 1 half times the 1 half gives a 1/4. If we move the 2 inside the square root, it becomes a 4. The 4 times the quarter becomes 1. Then we have the cross terms. We have minus half times gamma plus a half times gamma. They just disappear. And then we have the product here of gamma squared with a minus in front. So the minus gamma squared multiplied with the 4 that we moved in. So this just becomes square root 1 minus 4 gamma squared to the t. Okay. The square root just moves into the exponent as a half. So this is the in-sample error is no more than 1 minus 4 gamma squared raised to the t half. And here we can just use one last inequality saying that, well, that 1 minus x is less than or equal to e minus x for all x. This is a well-known inequality that's very useful here, which allows us now to say that the in-sample error is no more than, well, I'm just going to move this x here, the 4 gamma squared, into the exponent with the minus in front. So the 4 and the 2 turns into a 2. We have the t, we have the gamma squared. So the in-sample error of AdaBoost after t rounds is no more than e to the minus 2t gamma squared. And so they basically reduce the in-sample error very far down after t iterations. If you have this gamma weak learner in every iteration, something that has an error at most a half minus gamma. Okay. Now, what do we also know? We also know that the in-sample error is this weighted zero. Now, it's just the standard 0-1 loss. It's the average over all the examples of the indicator for whether the label is predicted incorrectly. Which in particular, we need one last trick. And the trick or the observation is that if the in-sample error is less than 1 over n, then it basically has to be 0, because any single term here, if it's non-zero, it is at least 1 over n. So if the in-sample error drops to less than 1 over n, then the in-sample error has to be 0. Okay, so let's just check now how many iterations do I need before the in-sample error becomes less than 1 over n, meaning that it actually becomes 0. So I have my guarantee up here. The in-sample error is no more than e to the minus 2t over gamma, t times gamma squared. And we just check when is this less than 1 over n. Taking log on both sides gives us just minus 2t gamma squared less than log 1 over n. Multiplying through with minus 1 flips the direction of inequality, and we can move the minus 1 inside the log. So we get 2t gamma squared is at least log n for this when this is satisfied. And finally, right, we can isolate t, and we get that whenever t is at least is greater than log n over 2 gamma squared, then the in-sample error becomes 0 actually, because it comes less than 1 over n and then actually becomes 0. So this is actually really neat. We have actually shown now that if in every iteration of AdaBoost, this weighted 0-1 loss that we get from the hypothesis we trained in that iteration, if this is less than a half minus gamma for all iterations, then AdaBoost will have 0 in-sample error after just log n over 2 gamma squared plus 1 iterations. There's only a logarithmic number of iterations in the number of training examples. So it's actually very few iterations. And then something that depends here quadratically on how small the advantage over random guessing is. So this is a really neat observation that actually managed to get 0 in-sample error, which means that it actually will turn any weak learner into a strong learner if we run it for enough iterations. Okay. So this was AdaBoost again. This is a really classic algorithm. And maybe let us just finish off by just arguing, just giving a little bit of intuition for why this alpha t was chosen the way it was, right? So this is, of course, not by coincidence. It is actually like a very clever choice of parameter alpha t. It's not just a magic constant. So let's just conclude by showing where did it come from? How did this alpha t come about? So, right. So basically the way that you can derive that this is the right choice for alpha t is that when we looked at bounding the in-sample error, right, we showed that it was bounded by the product of these normalization terms. And then when we were bounding the normalization terms, we did this rewriting of the normalization terms, where we ended up rewriting it as e to the minus alpha t times 1 minus the error t plus e to the alpha t times the error t. And this is the way that we rewrote it at the end, right? So this is just a couple of slides ago. We ended up with this rewriting. And of course, right, as we see up here, right, we want to make the in-sample error as small as possible, which means that we want the set j's to be as small as possible. So we want to minimize this expression here. All right, so let's see what happens if we choose alpha t to minimize this expression. So how can we minimize it? So as a function of alpha t, we have this expression here. We want to minimize it as a function of alpha t. And one first step that is, I guess, common to several of these minimization algorithms or things that we've been doing before is that at least if we can show that this is a convex function of alpha t, then we know that we can minimize it by computing the derivative and setting it to 0. So let's just first see that this is indeed a convex function of alpha t. So to prove that it's a convex function, we're going to use the rule. It's a function of a single variable. So we're going to use the rule that if the second derivative is a non-negative function, then it's a convex function. So let's try to see that. So we first compute the derivative. Using the chain rule, right, we get the inner function here is minus alpha t, and the outer function is e to the x. So e to the x's derivative is just e to the x, so we still have an e to the minus alpha t here, and we have to multiply with the derivative of the inner function. That's just a minus 1. So we get minus e to the minus alpha t. The 1 minus error t is a constant. Over here, the derivative is just the function itself, e to the alpha t. Okay, so that's the derivative. So now we compute the second derivative. And again, using the chain rule, right, this first e to the minus alpha t becomes minus e to the minus alpha t, and then we multiply with the minus that's already there. So we just get an e to the minus alpha t back. 1 minus the error t, and the second term doesn't change, e to the alpha t error t. And this function here, right, e to the minus alpha t, the exponential function is always non-negative. E to the alpha t is again non-negative, and error t and 1 minus error t are non-negative. So this is a convex function for all alpha t. Okay, so it's a convex function. So what we know now, we can minimize it by setting the derivative to 0. So we just set this expression here to 0. So we set the derivative here, take it down here, we set it to 0. So we move the left, this minus e to the minus alpha t to the other side. So we get e to the minus alpha t, 1 minus error t should be equal to e to the alpha t error t. And what we do now is that we multiply with e to the alpha t on both sides, divide by error t on both sides, and then we get e to the 2 alpha t is equal to 1 minus the error t over the error t. Finally, we can take logs, the natural logarithm here, and move the 2 on the other side, and then we get that we should set alpha t to be a half log of 1 minus the error t over the error t. And this is precisely what we had in AdaBoost, right? So AdaBoost is really choosing this alpha t in a clever way in order to minimize this product of these set j's. So this is why AdaBoost is doing what it's doing here. Good. So this concludes our theoretical study of AdaBoost, where we went through all the analysis and arguments for why AdaBoost actually turns a weak learner into a strong learner.